Hi everyone, I am Nadesh Tyagi and I'll be discussing formal verification of COLREG-based navigation of maritime autonomous system. There are a number of benefits to maritime autonomous systems. They can minimize the number of maritime accidents that are caused by human error and hence increase the human safety. The unmanned or lightly manned vessels will bring down the number of crews that are present on the ship and hence they will save money and they can eventually bring down the supply chain issues. The engineering benefits can be we can improve the communication and connectivity protocols. There will be new developments in these areas. There can be improvement in the sensor fusion algorithms, and we can develop novel modeling and verification methods, which I'll be discussing later. In this problem, we'll be introducing the notion of maritime autonomous navigation problem as a maritime reinforcement learning game. We have a standard set of navigation problem and we have a driving controller that will be synthesized in Opal Stratago. We will validate and verify the model as well as the controller using model checking in Opal. And in if every scenario they get verified and validated, then we'll be sure that collision has been avoided between the two ships. In this problem, we'll be using a standard case study as defined by COLREG. COLREG is just an organization that defines the rules on maritime navigation. So the rule states that if the two ships are on a collision course, so the ship that has the other ship on her starboard will have to alter its course to give way to the other ship. So in this case, the ship B has to alter its course by reducing its velocity, acceleration, its heading to give way to ship A while it stays true. We introduce autonomous maritime navigation as a two-player game in which ship B is our agent and ship A is part of the environment. The games can then be devised as reinforcement learning problems, and reinforcement learning is used for learning an optimal controller for ship B. A reinforcement learning problem is defined by set of states, set of transitions, and bad states and goal states. So these controllable transitions will be taken by ship B and the uncontrollable transitions will be taken by ship A. We have bad transitions in which the collision is unavoidable between the two ships and the goal states wherein we successfully avoid collision between the two ships. The controller for ship B is synthesized as a finite state, infinite time automaton which consists of a sensor which monitors at every time t whether there is a ship available in the vicinity or not. If it does not detect a ship in the vicinity, it goes back to the not detection state, but if it does detect a ship, it will have to change its course. It will change its course depending upon the specifications of the velocity, acceleration, its heading, and whether there is a wind or not. The model of ship B is also synthesized as a finite state, infinite time automaton. Initially, the ship B is in the moving state, and at t is equal to 0, it goes to the adjustment state, and if it receives a detection in the controller of the model B, then it goes to one of these states depending upon whether the angle has changed, whether there is wind, whether it has been deviated from the course, whether adjustment has been done or not. The controller gives the commands for the velocity, the angle, and the acceleration to change the position. The model then updates the position and the maneuver ends. It then goes back to the moving state and then again t is equal to 0, it goes to the adjustment state. If it receives a false in the detection state, it goes back to the moving state and it has steered cleared of the collision. The model and controller of both the ships in autonomous maritime navigation problem can be verified through Opal strategic queries, and if the result of a query becomes satisfied, then that means we have avoided collision between the two ships under all scenarios. On running different types of queries, we saw that the result became out to be satisfied. On running a strategy safe and not ending up in an end state, which is a collision state, the result of the query was satisfied. If we tried a different strategy that was the optimal safe strategy in which we tried to minimize the fuel consumption under 200 time units and the maneuver ended in a safe state, the result came out to be satisfied. On running a different query which involved windy weather and optimally safe state, the result came out to be satisfied. This paper made many novel approaches. It introduced the concept of maritime autonomous navigation as an RL game. It was the first paper ever that introduced any type of weather in their models. It also integrated fuel consumption by the ships and navigation mistakes by adversary vessel, which are maybe human errors in their controller actions for practical purposes. They have a drawback in their approach that they use fixed waypoints, which means that even after the ships avoided collision, the agent, the ship B, goes back to the same route. The author suggests that they could include multi-vessel navigation, winter weather integration, and involvement of other obstacles in their models as future work. I suggest that they also include effect of tides on motions of ships and time constraints in maritime shipping as future work. Thank you for watching.